Sit down at the table, please. Come on, guys, at the table, please. Yeah.
We had a new baby.
Yes.
You're a ham.
Did mommy feel a kick yesterday for the first time?
Yeah.
Dylan, hold hands. Bye-bye, guys. Say bye-bye. Bye-bye. Big wave. Bye.
I left Hawaii to come to Fermilab. I remember the first day because it was at a time when one of the big programs we were doing here was just getting underway. So when I showed up here, there was a laundry list of things that weren't working. And so it was just, here, jump in, grab something. This is going to be your thing. You make this work. So excitement is kind of an understatement. From day one, it was, okay, well, it's time to start learning.
We are a discovery laboratory. What we do is to get an understanding in terms of the basic constituents that make up our universe and the way in which those constituents interact with each other. Our laboratory is an Office of Science laboratory that's designed basically as a mission to look for those things that essentially you don't find in most any other laboratory in the United States.
Fermilab is an incredibly exciting place. It's a huge center of just physics, energy, stuff happening. And that's both in theory and in experiments. So intellectually, it's very exciting. Extreme cutting-edge research, brand new knowledge. We have three frontiers of fundamental physics. All three frontiers are addressing the fundamental nature of matter, energy, space, and time, but they do so in different ways.
The cosmic frontier has to do essentially with the connection between the particles that we look at here and the particles that are produced naturally within the universe itself, that is, within the cosmos, with galaxies and galaxy clusters and black holes are all connected to the fundamental particles that we can produce in our laboratory.
The energy frontier is the one most familiar at Fermilab, where we smash together particles at extremely high energy and see what comes out, probing very small scales, the interiors of elementary particles.
And that requires large accelerators and large detectors to go along with those accelerators and an incredible amount of computer technology to analyze the data that we collect. And the other frontier is the intensity frontier. This is a frontier that allows us essentially to do studies in high energy particle physics that may be extremely rare in their reactions. The reactions are so rare that we don't see them readily. So to be able to produce them, we have a high intensity particle beam, hence the intensity frontier, and this allows us to do millions and billions of reactions and ferret out just a few of these very rare reactions that are the science that we want to study. It's somewhat like having a small needle in a haystack, and the haystack is actually in a field of hay, and it covers 3/4 of the planet. But you're looking for that one needle. So the three frontiers cover the vast size of the universe, the accelerator area that we can actually control, essentially the building of the components that make up that vast universe, and then of course the rare reactions that happen in the universe with our high intensity beams as we see in the intensity frontier.
That ring out there, the Tevatron, was the largest superconductor ever built. So big you can see it from space. You can see it in your airplane if you're flying in and landing at O'Hare. And that's how we looked for new particles. We looked for new things at higher energies than anyone had ever looked before.
This is just what happens within a research facility. When you finish some part of that research activity, you finish, you do something else. And that doesn't mean that you build another laboratory. It means you come up with a different idea to use the infrastructure you already have.
So where we're standing now is in the antiproton production complex. What we're in the process of doing is converting these accelerators into a muon production complex. And it just turns out we have all this infrastructure that we put into making antiprotons. It's just right for making the type of muons that we need. And we're going to make one of the world's greatest muon production facilities in these rings, in these tunnels, and we're going to do some of the best muon experiments that have ever been done. We're going to push the envelope orders of magnitude compared to what other experiments have been able to do in the past.
We push the envelope. We do new things here. If you have an imagination, if you can come up with new types of things and new ways of doing things, this is a place to be. I think the future of Fermilab is inevitably tied to doing new things, having new ideas, exploring those ideas. Some of those ideas come up to be things that actually take you down a path that you never thought of doing before. And this happens in high energy physics all the time, like the World Wide Web and using neutrons for cancer therapy. And all these sort of things happen because we have some very imaginative people at Fermi Laboratory who say, I wonder what would happen if I did this. And many of those questions, in fact, in our business, most of those questions lead to a discovery.
Fermilab is a lot like a car. Your car's got a lot of moving parts. When you buy it brand new, it works beautiful and you love that new car smell. But if you don't maintain it, after 10 or 20 years, you haven't changed the oil, you haven't changed the air filter, it's not going to be running very well, if it runs at all. We've got 13 or 14 miles of equipment in the tunnel and thousands and thousands of devices in there. When they're running well, nobody ever wants to turn them off, to work on them, to maintain them. So we end up usually running them at just as long as possible until we have to shut down, because when we're running, we've got thousands of volts, thousands of amps powering all this equipment in the tunnel. Nobody can go in there, but eventually we have to go in and work on things.
Normally the accelerators run 24 hours a day, 7 days a week, continually providing beam to the experiments. However, usually about once a year we shut down for maintenance and sometimes for other upgrades. Lots of different jobs.
So this is a bird's eye view of the Fermilab site. You could see all the different rings, which are different accelerators, and all the different lines, which are beam lines. And right here is Wilson Hall, our high-rise. Everything starts right on the west side of Wilson Hall over here. So we start out with a bottle of hydrogen, and that's where we get our protons from. So we pull them out, and we bring them down this first accelerator here. This is our linear accelerator, where we pump energy into there, and as the particles travel down the accelerator, they get faster and faster and faster. Now the problem is, if we wanted to get them as fast as we need to get them, we'd have to make this linear accelerator really long. So instead, at the end of the linear accelerator, we shoot the particles into a circular accelerator. Our first circular accelerator here is called the booster. And each time the particles go around the booster, they get faster and faster and faster until they get to the maximum energy that we can get them in the booster. So after that, we take them out of the booster, we bring them into this ring here. This is the main injector. We play the same trick as they go around. They get faster and faster and faster until we get them up to the perfect energy, the sweet spot for doing different things with them. So one of the things we used to do with protons in the main injector is we'd shoot them into the Tevatron ring. And we'd also shoot them over here, make antiprotons, and shoot those into the Tevatron ring. We'd bring those together in different collisions at the CDF experiment and the D0 experiment, and we'd search for new particles in the proton-antiproton collisions. These experiments have been running for a long time, CDF over there, D0 over there. We've been taking data like gangbusters, and now we've got billions and billions of events. So all that information is now on tapes that are all sitting in the computing division. Even though the experiments aren't running anymore, the next step is really going through that data again and again and again. Are there new things, new particles that we could find? Is there information that we have that can help the LHC? If the LHC discovers something, can we come back and say, what information do we have here? The two data sets together is going to give us a lot more information. So it's gold. It's Fort Knox over there. That's our Fort Knox. And that's a process that will go on for the next decade. The other thing we can do with protons in the main injector is we can shoot them into different beam lines and smash them into the different targets and get all sorts of different things coming out and have different sets of experiments in all these different buildings that you see along these beam lines here. Now, something that we've only started doing in the last decade and what we'll continue to do is take protons out of the main injector, shoot them into a target, and make a beam of neutrinos. And so we have a neutrino beam line here that goes all the way to Minnesota. And then we're going to have a neutrino beam line that comes around here and goes all the way to South Dakota for neutrino experiments out there. So with this complex of accelerators, we could do just about anything you'd ever want to do with protons.
Especially in the accelerator division, we rely more on technicians and operators and engineers and probably than any other group at the lab. The physicists are very important when the machines are running and for figuring out what we want to do next, how we want to design our new machines. But during a shutdown like this, and even when we're running and things break, it's absolutely critical that we have a great group of technicians.
A lot of people think that Fermilab is a laboratory that's just physicists, a bunch of people in lab coats just doing physics research. And in reality, they're not the majority of the people here. No physicist makes this equipment, installs the equipment, and maintains it. That's done by machinists, it's done by engineers, a lot of technicians to maintain and install and upgrade the systems. In addition to that, of course, we have all the people keeping the whole lab running. High voltage electricians, mechanics, somewhere there's an accountant that pays me every month. I don't know how that works, but this is a very diverse group of people here.
That's one of the things I really love about Fermilab is I think everybody takes pride in their work. It's like my feeling is that we're a big happy family, and we all work together for the good of Fermilab. So that's one of the things I really like about this lab.
Okay, let's go. Sam, do you want to pick out a spoon and a bib? Okay, bye-bye, Sam. Bye. My kids make me a better physicist. They certainly teach me time management, and I may not work the fabled 80-hour week, but I sure eke every minute out of every day that I'm at work. How are you? Good, how are you?
A very special way that Fermilab works is teams of scientists. So they have in their DNA the desire to work together as a team. And that is a very powerful thing. It means that you could do very large, complicated, challenging projects that you couldn't do anywhere else. At a place like Fermilab, even beyond the borders of the lab, in collaboration with universities across the country, labs around the world. Fermilab is involved with all of those things.
If we break the world down into the smallest possible parts, the smallest parts we can come to are elementary or fundamental particles, and there are 12 of them, and 3 of them are the neutrinos, and they come in 3 different flavors: the electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are fantastically interesting particles, but difficult to study. They're electrically neutral, that's the neut part of them, and they're very tiny, that's the eno part of them. So neutrinos, electrically neutral and very tiny. So this is argonute, it's a neutrino detector. You never actually see a neutrino in the detector, you see the remnants of what happens when a neutrino hits something in the detector. Now the thing that complicates neutrino flavor is the fact that neutrinos oscillate between their different flavors. I can create a neutrino beam that's purely one kind of neutrino, and it can spontaneously morph into another flavor of neutrino. Let's think of an analogy for neutrino oscillations, and we can think about one of my children's favorite topics, which is ice cream. So you start at the ice cream factory with your 3 standard flavors of ice cream: strawberry, vanilla, and chocolate. And you drive from the ice cream factory to the ice cream store, and what you don't anticipate is the time it took to drive the truck to get to the store. Some of the strawberry becomes chocolate. All of the strawberry and the vanilla become chocolate. That would be my children's preference. And that's what neutrino oscillations are. Your 3 flavors of neutrinos change. And so you measure them at the near site, what they started at the ice cream factory, and at the far site, what you actually deliver, and that tells you different properties of neutrinos. And that's the revolution in neutrino physics that happened just over a decade ago. Sorry. Yes, now we're trying to study how matter is different than antimatter. That's the holy grail. We live in a matter-dominated universe, and we don't know where the antimatter, which should have been created in equal amounts in the early universe, went. So we study neutrinos to understand that.
Discovering that neutrinos were the source of the disappearance of all of the antimatter that must have been produced at the Big Bang, that would be a great discovery for science, because it's one of these questions that, this is such a fundamental principle that matter and antimatter get created in equal portions, and it's sort of embarrassing that we don't know the answer yet. Why it is that there's this huge imbalance between matter and antimatter in the universe. It's like, if you can explain away so many things, why is the sky blue and all this kind of stuff, but you can't explain why there are no antiparticles around. So that's why it would be a really great discovery for science.
I want to see neutrino interactions. It's so exciting just to see these beautiful images of neutrino interactions, and to see that we can get these detectors up and running easily. Someday we want to build a really big one. That's the goal of building these detectors from the smallest scales to learn as much as we can up to the biggest scales, high-rise size detectors, so that we can look for matter-antimatter asymmetry in the neutrino sector. The Holy Grail will take many years, so it's a process, and the process is just as much fun as the eureka moment, maybe even more fun. I never imagined as a physicist that I would work deep underground. It's kind of fun to do so. You have to take an elevator that goes down 100 meters from the surface, and it rattles as it goes, very industrial. Neutrinos pass through the Earth nearly unnoticed. So we don't actually have to build a beamline between Fermilab and Minnesota. We can just let the neutrinos travel through the Earth, streaming through like little ghost particles, like they travel through the Earth all the time, until they get to the detector, where we hope some of them stop.
The whole purpose of Minerva, I should say, is to study how neutrinos interact with matter. And it turns out that the atom that it's interacting with has a big impact on the type of interaction that occurs, or the way the interaction happens. The final look of the interaction will be different if it happens on iron versus on water, versus on lighter elements like hydrogen or helium. And the purpose of the experiment is to study those types of effects. In the future, we're going to do the next generation of oscillation experiments. Well, what kind of materials do we use in the neutrino oscillation experiments? We use iron and water and these types of materials. And it turns out water is used pretty commonly in neutrino oscillation experiments, so we decided to design and construct this object. So the tank is full of water. So what that means is there's a whole lot of hydrogen atoms and a whole lot of oxygen atoms. So when the neutrino enters into the water volume and one of them just happens to interact with either the hydrogen or more likely the oxygen atom because it's bigger than the hydrogen. If you think of each nucleus as a set of billiard balls, where the oxygen would have 16 billiard balls all grouped together, but you can't see the pool table. There's a sheet blocking your view of the pool table. But if somebody on the other side of that sheet hits the cue ball, our neutrino, hard enough into the racked oxygen nucleus, and you're standing on the other side and you see, aha, the 7 ball, aha, the 4 ball, then you can deduce what happened on the other side of that sheet. And that's basically what we're trying to do with this detector by looking for what kind of particle comes out of that neutrino billiard break.
Now, something that we really don't understand at all is that neutrinos oscillate like crazy. Quarks oscillate, not as much as neutrinos, but they still oscillate. No one is yet to see a direct transition from a muon into an electron, or an electron into a muon. So that's one of the things that we want to find. A muon is 200 times as heavy as an electron is. And we have no idea why. If you have a muon just transitioning straight into an electron, this just violates so many laws of physics that we have, because the laws of physics have been built up to say that this can happen. So we want to reinvent the laws of physics. And if we discover this process, it'll force us to reinvent those laws of physics.
I think theorists are quite emotionally attached to chalkboards. There's also the question about whether you want to use a chalkboard or a whiteboard. And my answer to that one is chalkboard's better because you can stand there holding your chalk for a long time while you're thinking about what you're going to do, possibly not saying anything, but just standing there. If you're holding a marker pen, it dries out while you're standing there. And chalk's ready to go when you're ready to go. Solving the mystery of dark energy is a huge challenge because we don't know what dark energy is. Dark energy not only pervades the galaxy, it pervades all of empty space. So all the space between the galaxies is full of dark energy. Dark energy is the energy that is in the vacuum, in the emptiest space that you can make. You could describe it as a new kind of energy, or you could describe it as a new kind of gravity, and we don't know which it is. So we're starting by looking more carefully at the expansion of the universe and trying to see whether it affects the growth of structure or has some other effects on those large scales. Basically, by making more precision studies of the universe as a whole seems to be the way to start. Well, the dark energy camera is just like it sounds. It's a camera, and we're going to use it to study dark energy. It's a very large camera. It has 500 million pixels, and it's super precise, and it's going to go on a large telescope. It's going to go on a 4-meter telescope in Chile. So it'll see deeper and wider than anybody's ever seen before. It'll look very deep into space. And over the course of a few years, we'll get pictures of about 1 billion galaxies with it.
This is the camera. You can see it's not very lightweight or easy to carry around. This thing will be mounted on that thing, which is called the barrel. The camera actually bolts to the top of it where the hook is hanging right now. And then that whole thing gets picked up and put into the cage and mounts to the hexapod. And then we take it all apart and ship it all to Chile. And then we do it all again, but then it's on the real telescope. So this is our model of the telescope. The rings that you see up on our telescope simulator match these 2 rings that are at the top of the telescope. This shows you how the whole thing ends up fitting together. The CCDs in this are cooled to liquid nitrogen temperatures, and that makes them very, very low noise and very sensitive.
With the dark energy camera, we can't actually take pictures of dark energy. At least we don't think so. It doesn't emit light, it doesn't absorb light. However, the dark energy has gravity, and the gravity affects the motions of things. It affects the motions of galaxies, it affects the motions of light. And the light we can see with the dark energy camera. So what we're looking for is very subtle effects on the light of many, many galaxies. And we think that these overall properties of the empty space between galaxies will have enough of an effect that we can tease out the effects of dark energy.
Now we know that the visible stuff is only a few percent. Dark matter is about 20 to 25%, and dark energy is 70% of what makes up all the stuff in the universe. They call it dark energy and dark matter because you can't actually see it. Nobody knows what it is, and there's lots of people coming up with crazy ideas, and so we really need data, and this is going to provide a big chunk of data to help us understand that.
We think that dark matter is left over from the early universe. There's a lot of indirect evidence and arguments for that. So we think it's some new kind of stuff, a new particle, that's never been seen directly except through these gravitational effects. And so you might ask, well, you can't see it, so how do you know it's there? And the answer is we only know it's there because of its gravity. If it weren't there, the galaxy would fly apart. So you have this indirect evidence that it has to be there, and there's a whole lot of it, but we want to look for it.
It should never come back any higher than it started as, because that would break conservation of energy. Raise your hand if you think he's going to lose his nose today. Oh, Dave, they're betting against you.
Here goes.
Are you okay?
Okay, so that's conservation of energy. It can't come back with more than I left with, thank goodness.
The bison are a symbol of the frontier, right? So the American frontier, the untamed Wild West, that was part of Wilson's vision scientifically, and the bison are just an instantiation of that, an enduring symbol.
Robert Wilson actually designed this building, the high-rise at Wilson Hall. You know, he was inspired by a cathedral in France somewhere, and so the idea is that in the cathedral, you walk in and it's, you know, broad at the bottom and then narrow up at the top. That's what he was inspired by, and it is a really beautiful building. A huge number of countries send physicists to Fermilab to do these experiments because it's one of very few places in the world where they can be done. And so all of these flags represent all of those different visitors who are here at the lab doing experiments.
This is the Fermilab Remote Operations Center. So this provides a place for scientists to participate in the CMS experiment. It's really exciting being involved on a project of this scope with collaborators around the world. You feel that the global nature of this project every day as you think about even the time difference, the 7-hour time difference. Here in Batavia, we're 40 miles outside of Chicago, but we're 4,000 miles from the experiment location in Geneva. And we can do a lot of the same things that are done in that control room, we can do in this room. One of the things people notice first when they walk in is a 24-hour-a-day live video connection between the different control room sites. And so this live video display lets us communicate with our colleagues at the different remote and central control rooms.
If you ever wave, do they wave back?
Hi, can you hear us in the 0.5 control room from Fermilab?
Yes.
Hi. So, yeah, sorry to interrupt. If it's okay with you, can you step back a foot or so and wave hello?
Okay.
There. Okay. Hi. There's a lot of people like myself who actually are working on both experiments in Batavia and at the LHC. So right away you can tell we're pushing for both of them. We'd like both of them to succeed and are excited about developments at experiments at either site. We're here monitoring the data on the front lines. We see things as they come in, and occasionally we'll see an event that flashes up on a screen that looks interesting. Then we know we're going to have something interesting to look at in our physics analysis. It's important for Fermilab to continue working on the energy frontier experiments, which are right now starting up at CERN, so that we maintain our involvement in the forefront of this research.
Well, we're satisfied that with the structural integrity of the tank, and now we put it on a truck, take it over to the new near detector hall, lower it down a shaft 330 feet, take it down to the detector and hoist it up and slide it into the small 11-inch gap that was left specifically for it, and then refill it with water, and we'll have our water target. These guys are going to very carefully bring it down this shaft and drop it down into the slot that we've left for it. I can't believe how close that cross beam is. That'd be good.
You never know the problems you run into, but we were able to work it out. And Bob's happy, we're happy. You happy? Good.
They actually fit pretty well, so I think we got it.
The gap here is about 11 inches, and you can see that the water tank is using about 9 of those. And sure enough, they got it in safe and sound, and we're able to squeeze it in to its final resting spot.
The next step will be to fill it with water and start looking for neutrino interactions. There I am right there. Dave Schmitz. Oh, and my mom was in town, so I signed for her.
The most exciting time is when you first turn on an accelerator. It's like the first time you worked on your car, you did something like change the transmission yourself. Now what happens the first time you turn that key?
Sad.
The first way you know the shutdown is a success is you're able to turn back on again. But, you know, there's a huge number of people in the control room the past couple of days, which is a clear sign that things are going and everybody's excited to get everything back up and running again.
So it's looking good. Yes. Everything's positive. It's clear we didn't break anything.
It means data. It means that we can sit back and watch the data roll in and do the analysis, and so it's great. It's really, in a way, it's a less hectic time than during the shutdown because we just run. We just take data, watch it come in, make sure everything looks good.
So things are starting to really come up now. So we hope to complete tuning up the main injector today, and that's sort of the gateway to all the other machines. So now that we're able to get beam through the main injector, we can send beam to all the other machines. Probably by this weekend, we'll be back to regular operations.
So far, it looks like everything's very good. It looks like it's going to be a very exciting turn-on period and be a very exciting year of accelerator performance.
Is it weird for a physicist to be into sports?
No, not at all. It seems just as often that I, mention that I play softball or other sports while I'm at the lab. Some turn their noses and other people are ready to sign up and join you the next weekend. I get, universally the same response from my friends and teammates and whoever else I meet here in the city when they find out that that's where I work. And that is, oh, can visitors come there? Can I come and see it? Like, I've heard about it. Those who are from the area might say, I went there when I was in 7th grade, but, not since. Or I've heard about it, but never seen it. And everyone, pretty much across the board, requests to come out and visit. And I always say, anytime, come out anytime.
I would really love it for science to mean in this country the scientific method and questioning everything and wanting proof of everything. Unfortunately, in this country, I think science is this, it's this really tough thing that you have to be so smart to do. And first of all, that's not true. It's really not true. You have to work hard. You have to be familiar and comfortable with math. But you don't have to be a genius, right, to be a scientist. I can tell you. You don't have to be a rocket scientist to be a scientist. We need more people who understand science and logic and are able to make educated guesses or to know when they don't have enough information to make educated guesses. And I think we need those kinds of people in government. We need those kinds of people as doctors, as lawyers, as judges, as politicians. We don't need them just all to be scientists.
When you're doing science at these different frontiers, what you find is that the technology just doesn't exist. We need faster computers, better materials, stronger materials, lighter materials, more flexible materials.
You meet those challenges and then they propagate out into the rest of society and raise everybody's standard of living.
I was in Greece this summer for a conference on neutrinos. It was a whole conference all on neutrinos. And while I was there, I went to a store that sold all these things for made out of olive wood. And apparently olive trees take like 50 years to bear fruit. And so it's not even something you do for your children. You don't plant an olive tree because your kids are going to get the olives. You do it because your grandchildren are going to get the olives. And to me, I think that's kind of what we're doing in particle physics. We're trying to understand the universe, and maybe somewhere down the line, our grandchildren will realize, you can use this and build another World Wide Web, or they'll understand what to make of these measurements that we're doing now. They'll figure out some theory that it knits everything together and makes sense.
The reason for doing this kind of work is so that we can actually learn something new. And we do that almost every day, but Fermilab has the capability right now of basically changing our whole view of the universe. And quite frankly, if you do have the knowledge to understand how the universe is put together, you might actually solve some of the problems that we have. I'm always fond of saying that the work that I do solves problems that we don't know we have yet. It may not actually solve the problem that we can identify today, but 50 years from now, it might be exactly the piece of knowledge that you have to help you survive.
We have the facilities, we have the ideas. The sky is really the limit, and it's a very exciting time to be a scientist here because you get to be a part of the answer to the question of what's next.